particle path. It's important to understand this distinction because the equations that define both the streamline and the particle path are looking somewhat similar. They are similar. You have to understand the difference. So we point out that the streamline is a curve in space in such a way that the tangent vector to the curve at any point is the velocity vector. Curve in space, so that the tangent vector at any point on the curve will give the velocity vector at that point. So I can write the defining equations for streamline. Suppose the streamline is given by xi of tau to b. So tau is the parameter that will describe the streamline. We've seen any curve in space, very general way of representing it is by a parametric representation of this form in three-dimensional space. So the tangent vector in this way I've already seen is given by dxi by d tau ei. So we can simply equate this to bi ei. There's no need to use symbols. Summation in this, that's also fine. Right? So this is what we have. So the defining equation for the streamline is given by bi. That of course can be a function of time also. Velocity can also be a function of time in unsteady state flow. But whenever I talk about streamline, keep the time fixed, right? Keep it as p bar instead of p naught because that this has really nothing to do with the reference configuration. So any time you freeze the flow, right? So then you can form the streamlines at that instant. So these are curves in space. So the moment you say that the tangent is tangent to the velocity vector can in general depend on time, right? So we have to fix the time. Then we get a well-formulated problem that will allow you to integrate this set of equations, some function of x1, x2, and x3. And then we need an initial condition. So I need to specify one point on this curve. So I want to look at a curve, let us say streamline, let's say passing through x0. Right? I want to describe the streamline passing through that. And I can arbitrarily choose the parameter tau. Here to be tau equal to 0. That's totally arbitrary. And then I say that then if I solve the system of equations, then I will get the streamline passing through the point x0. Right? So that's what I will get. So the particle path is nothing but described by this equation, xi equal to, which we started out with defining this relationship between the material coordinates and the spatial coordinates. Particle path is essentially the path traced out by the point psi, right? And let us say some time t equal to 0. Suppose let us say at time t equal to 0, right? The coordinate occupied by a point is psi. Then I can ask what will be the path traced out by that particular point. Right? So this is now something that happens in time, right? So we have seen that the reason why the equations look the same are because we are taking the velocity directly. It's a tangent to the streamline, so it will come into play. If I now want to calculate the particle path, I need a differential equation that describes the particle path, and we have seen that the x by dt of psi t is the way we actually define the velocity. So now if I write this out in all the three clearly dx by dt means psi is kept fixed. That's exactly the situation we have here. So I can now write the equations to determine the particle path as dx by dt is equal to di. This now will be given in terms of x1, x2 and x3. That's what is how it is available. This again can be a function of time. And now the initial conditions for this is xi at t equal to 0 is, let's say, psi I equal to 1, 2, 3. So my initial point is this. Then I have to integrate and see how this particle is going to move in time as well as in space. Right? So this motion is actually in time. But then I want to plot it on the as a curve in space. For instance, we have the parametric representation of a circle at a cos theta. Here, x is a function of theta, y is a function of theta. But when I actually can plot it as theta versus x, theta versus y, it's going to be an oscillating function. We don't get anything from that, right? But however, if we plot it on the xy plane, then I'm going to get a circle. Theta sort of disappears from the picture. We get a curve in space. The same way, the time here actually acts as a natural parameter. So I get the particle path. So this will be a function of, once I fix psi I, this will now be a function of time. The solution to this will be x1 of t, x2 of t, x3 of t. What we mean by a particle path, I can also plot it separately. T versus x1, I can plot it like this, but what I want to plot is like this. On this three-dimensional space, right, I want to plot this behavior. So clearly time will be suppressed and I will get some curve in space. So this is how the streamline is. Not streamline, the particle path is constructed. So the time is very much there. There you freeze the motion in time and get streamlines. Here we are following the motion of the particle with time and then plot it in space. We get the particle, but there is no reason to require the two will be actually the same. Right? And now Aris actually has given a couple of examples. We take one of them. He says that the two will be the same when you have steady flow. Let's now take one example he has given. There clearly may not correspond to any real practical situation, just a textbook example to illustrate the point. So according to him, the velocity is given by this. So v1 component, first component is given by x1 by 1 plus p, v2 is x2 by 1 plus p, v3 is x3 by 1 plus t. T is the time. It is not 3 but t. T is the time. Right? So now you have to obtain the streamline as well as the particle path. Now you will see how they differ actually in the calculation first of all. So first to get the streamline, the equations are there. dx by d tau is equal to di. Right? So xi by 1 plus, I want to fix the time. So that's very important, otherwise you end up integrating with respect to time. You end up actually getting the particle path. Right? So it's important to fix that. So it's very easy to integrate this. And the important thing is the qualitative, the nature of the differential equations for unsteady flows different here as compared to here. Here the right hand side is not a function of the variable with respect to which time having the derivative. Whereas here it is. This is a distinction between what are known as autonomous systems and non-autonomous systems. Right? Where the right hand side depends on time. It's obviously a more difficult case to integrate, right? Than if it doesn't happen. Right? So this is what it is. So now I have to integrate this. So it's very easy. So I get dxi by xi. I can do it one by one. Again, I can choose some initial condition. I'll take this as the initial condition. So I can write this as, and this would be again make this the dummy variable. We can put a prime for the dummy variable. So this would be basically log xi by xi naught is equal to tau y1 plus t bar.
So yes, for this differential equation, t bar is a constant when we get tau parameter.
Yeah, t bar is a constant, so the tau parameter it just comes out. It's very easy to integrate. Right? There's nothing on the right hand side, it depends on tau, so I can integrate it very easy. So this is what it is. Right? So I equal to 1 to 3. So all of them will be the same. Because the form of the velocity is very the same for each one of the velocity components. So this gives me the streamlines. Right? So now this is a curve in space. So how would it translate as a curve in space? Because this is each one, right? Expressed as a function of tau. But what I want is an equation which relates only x1, x2, and x3. How would you obtain that? What would be the equation? Yeah, exponential even I don't have to do because basically log of x1 by x1 naught is the same as log of x2 by x2 naught. The same as log of x3 by x3 naught. So I can write this as x1 by x1 naught equal to x2 by x2 naught. This is the, finally I have to get this. You cannot just leave it like that. What do you think this corresponds to? In 3-dimensional space, what type of a curve? No, whenever you need a quadratic curve, yes. It is, what would, let us say x1, x2 plane, what would this correspond to? A straight line. You have now another equation that will also be now a straight line. Right? If I leave it like this, it will correspond to a plane in 3-dimensional space. Now I have another restriction. This is the equation of a straight line in 3-dimensional space. Right? It is in fact passing through the origin. If you put x1 equal to x2 equal to x3 equal to 0, right? It will satisfy. So straight, bunch of straight lines passing through the origin. Right? That's what it is in space. Right? Depending on the value of x1 naught, x2 naught, and x3 naught, we get different straight lines. Right? So that is what it is. Now what can you say about the particle path? So this is the streamline. They are all straight lines. Particle path. Particle path would be dxi by dt is equal to xi by 1 plus t. That is what it is. Now you will see if the t were not present and it corresponded to steady flow, then there would really be no difference effectively in terms of the integral. Here, though, I have to look at it differently. So this is again dxi by xi is equal to dt by 1 plus t, right? And so I can again integrate from 0, let's say. And so xi would be psi I, right? And then this will be xi 0 to t. I'm now imposing the initial condition. Or you can integrate it out and use the initial condition to calculate the integration constant. I'm just doing it diagonally. Right? So clearly now this is log xi by psi I is equal to, this is log of 1 plus t. And at t to the 0 is going to be log of 1 because 0, log of 1 plus t. Again, I into 1, 2, 3. Aris actually says, now the question is, are these two the same? Are do the streamlines and the particle paths in this case, would they coincide? Because that's what he asks you to prove. Do they look the same or different? They look the same or different? Because I have told you, he's asked you to prove the two are the same. You're saying it looks the same. So actually, I would say the answer is wrong. It doesn't look the same, but effectively they are the same. He is not quite a constant here, right? He is not a constant. It's very important. It's not a constant. However, what I want is a curve in space. Now, how would this look as a curve in space? Right? This would again look as xi by x1 by psi 1 equal to x2 by psi 2 equal to x3 by psi 3. It's exactly the same as this. Only the constants are different. What this means is that I can always choose my x1 not, x2 not, x3 not to coincide with this, so that for every streamline I can identify the corresponding particle path. If you got a whole bunch of streamlines and a whole bunch of particle paths, they will basically look the same because those are also streamlines passing through the straight lines passing through the origin. And you can always make a mapping between a particular particle path may not correspond to a particular streamline, but I can always find a streamline that corresponds to a particular path by using the material coordinates suitable. So here is an example. In fact, what he is given it probably does that steady flow the two would be identical, but unsteady flow in general they are not expected to be the same. However, in this special case, they are effectively identical. So the particle paths come out the same as that of the streamlines. Right? So, even if the equation here looks a bit different, on the face of it, the integration will be different. Because there I have to take the time into account during the integration. Effectively, because if I need project it onto the three-dimensional space, even though here time is an important variable, here it is a tau that characterizes. So when I parameterize here, I will effectively get the same type of behavior, namely straight lines to the origin. So in that sense, particle paths and straight lines here, in this case, even though this is an unsteady flow, because the velocity is depending explicitly on time, it is a special case. But normally, probably will get an example and find it in the assignment where you will get a case where they are not the same. So this should clarify not only the distinction between the streamline and the particle path, but how you go about calculating them. So are there any questions? Yeah, how is the parameter? That's what, it doesn't matter. Either right is finally I found an equation relating x1, x2, and x3.
That will be constant at a point. At a certain point in time. x1 is equal to x1 by x not.
No. You have to look at it as a curve in space. Right? As a curve in space. Whether we write it as logarithm of x1 by psi 1 equal to logarithm of x2 by psi 2 equal to logarithm of x3 by psi 3. Or as x1 by psi 1 equal to x2 by psi 2 equal to x2 by psi 3. They contain the same interval. Right? So that is the point. You are describing a curve in space, and that's exactly what should be the final result of all these integrations. Should be. Then only you can compare whether the particle paths are the same as that of the stream.
But it won't be a straight line forward.
No, it's a curve in space. Right? And the equation is x1 by x1 not equal to x2 by x2 not equal to x3 by x3. And that is a straight line. That's not. Tau doesn't come into the picture. Here, finally, when you plot it, finally we want it plotted not as tau versus x1 or tau versus x2 or tau versus x3, what is it is translating as a curve in the three-dimensional space. You have to write that down finally. Right? So then you see actually what type of a curve it would describe, and I just don't plot that curve. Parameterization is only a tool to get to that. Just as plot a circle, x equal to a cos theta, y equal to a sin theta is a method to obtain. Right? So you choose a particular value of theta, calculate x and y, and plots that point. Finally, when you trace out the curve, you only look at the curve. Right? That is the point, which is x squared plus y squared equal to a squared. So I forget about how I got there. Any other questions? Okay, we'll now move on to another sort of a small topic which comes by the name of the so-called Bernoulli theorems. So the Bernoulli theorems, a certain group of quantities or a certain group of terms, right, all added together I will call as H, right, is a set of terms. The set of terms H, the notation used by Seren would turn out to be, maybe define it shortly, but H is given by this. The tensor form of H is given by P naught to P. I'll explain these terms shortly, but under what conditions this group of terms will be a constant? That's the question often answered by Bernoulli theorem. To get to that, first I will consider a case of we have to look into the continuity equation as well as the equation of motion. So the dental fluid continuity equation is given by dO by dt. If I don't restrict it to incompressible fluid, then I have to write the continuity equation. I am including unsteady flows also. And then the equation of motion is given by consider that before I go to the one important class of fluids we have considered are the incompressible Newtonian fluid. Right? But before that, I will consider write the Bernoulli theorem to consider what is called as a perfect fluid. A perfect fluid is defined by the following relation for the stress tensor. Namely, the stress tensor is entirely determined by the hydrostatic part alone. Something that has this form for the stress tensor is what is called as a perfect fluid. So there are no shear stresses, there are only the normal stresses, and those are given by the pressure alone. No normal component coming from the deformation tensor. So often that is why a perfect fluid is referred to as a fluid with zero viscosity, because when I put the viscosity as zero in the linearly viscous fluid, right, I will get this. That's one way of looking at it. Perfect fluid really doesn't have to be connected with the viscous fluid. One way of referring to it is as a fluid with zero viscosity. Right? So the linearly viscous fluid has the two types of fluid we are now considering for the Bernoulli theorem. Okay, so that is the linearly viscous fluid. This is the perfect fluid. Now for the perfect fluid, and we further assume that V can be written as the gradient of a potential. So we consider the conservative force throughout all of the statement of the Bernoulli theorem. That is where the phi comes in here. The phi that appears in the Bernoulli theorem. So we can now establish all the terms in the quantity h. This is P. Rho expressed as a function of P. I will explain it. I have to explain it. This is the phi. This is simply half V square. V square is nothing but V naught into P. So that's a scalar. You wonder what V is a velocity. It's a vector. What would V square mean? Right? We've already used this notation earlier. V square is simply given by V dotted with V. It's a scalar quantity h itself. Right? Now what about this? I will again explain that. Now for the perfect fluid, perfect fluid can also be either compressible or incompressible. Right? So if it is compressible, incompressible is very straightforward. Density is a constant. But if it is compressible, then I pointed out that P is equal to P of rho T. Now, in this case of the Bernoulli theorem, we generally assume that the temperature is fixed at some point, at some value, right? So that the pressure is dependent only on the density, or it might be that the dependence on temperature is not that much. We can simply neglect it, so that the pressure becomes expressed as a function of rho. All these conditions are built for the Bernoulli theorems, right? So what I am now considering as a special case of perfect fluid, right? So here we consider the case of the compressible fluid. Whenever we consider the case of the compressible fluid, this is what we have to deal with. If the fluid is incompressible, then the rho can be taken out of the integral. We come to that as a special case, right? So with all these qualifications, I can now write the acceleration as, if I divide rho by rho, then I will get minus the gradient of phi plus, now what would be the divergence of T if T is minus P times I? Simply the gradient of P itself, right? So it would be minus the gradient of P. So just the phi, you can also write it as plus the gradient of some potential, but it is conventional to bring the two together. So I can now write this. But however, the complication will come because the rho has to divide throughout. So the density is not a constant as an incomplete fluid. We have to somehow take that into account, and it is possible to show that this can be written as in that form that I have here, P naught times T. Now what is rho of P? Rho of P is the inverse relation which relates P to rho. I can also express, assuming I can express rho as a function of P, and it is possible to show that this can be obtained. What is interesting to see here is that the acceleration of a perfect fluid can be expressed as the gradient of a scalar, which we may regard as a potential for the acceleration. Right? And since we know the curve of the any gradient of any scalar is 0, we get that the curve of the acceleration is equal to 0 for a perfect fluid. And I can immediately simplify the equation that we wrote down earlier, namely the Bernoulli diffusion equation, can be simplified as follows. It implies the Bernoulli diffusion equation has the curve of the acceleration as one of the terms. That will drop out. The Bernoulli diffusion equation will become that set V2 because we have already got the diffusion equation. We didn't quite consider what would happen to the Bernoulli diffusion equation for an incompressible linearly viscous fluid. This is the form it would take for a perfect fluid. I'm not going to develop this because we want to get to. I've got this, but I want to get half V squared also. So for doing that, I will expand the left hand side and write dV by dt as plus d dotted with the gradient of V. That is simply the expansion. And then I'm going to use this important identity, vector identity that we have probably proved before, namely A dotted with the gradient of A, with A is any vector, is given by half times the gradient of A dotted with A plus the curve of A, the cross product of that with A. I'm writing it for A because I don't want you to confuse. I'm going to use with A equal to B. If you don't think that this is valid only for the velocity vector field, it's a general vector identity for any vector field. Vector field, I mean, it depends on the position. That's what I mean. Okay, that's when the curve and all that makes sense. It could be a function of time also. That derivative doesn't appear here. Right? So, in this equation, right? So, if I now apply it to V, right? So, I get E dotted with is equal to half E dotted with V, which I can write as V squared, right? Plus the curve of the velocity and the cross product with the velocity. Curve of the velocity is nothing but the vorticity vector, and so this is what I get from E dot the gradient of V. So when I substitute it here, I will get dV by dt, which is this. So this will be dV by dt, right? Plus the cross product of the vorticity vector with the velocity vector. Now I am going to bring this to the right hand side. Half of the gradient of V squared will now come into the gradient and with a negative sign because I'm taking to the other side. So this will now become minus the gradient of effectively h. Right? Minus the gradient of phi plus dt prime by rho of v prime. Right? I have to explain how I got here. Slide D2 involved, so I don't want to get into that, but you can show that P0 is any arbitrary pressure. Right? So I have got the h. Two terms of the h are already there on the right hand side here. The other term is coming from half times the gradient of v squared, right? And when it comes over here, it will become minus half times the gradient of v squared. So that can be taken into the minus of the gradient with a positive sign, and I will get minus the gradient of h. So this is the basic equation that will help us get the Bernoulli theorem. Now you can impose whatever condition you want. Now suppose h is to be a constant, that means the gradient of h must vanish. Right? If h is to be a constant, so that's what all the Bernoulli theorems effectively amount to. They all say h is equal to a constant. The conditions are important, right? Whether they are it's a constant throughout the flow field or not. So clearly, you can see that if I can first, if I want this to be 0, then these two terms should add up to 0. But it has to make some physical sense. So at first I make this 0. So I consider steady flow. Right? And then second condition I can consider is irrotational flow. That means W equal to 0. Of course, I can also consider that W cross V vanishes between the velocity is parallel to the velocity. You can impose that condition. Then also h could be a constant, but there doesn't seem to be any clearly identifiable flow that is very well known with those properties. Right? So irrotational flow is a very well studied special flow for which W equals to 0. So under these two conditions clearly, which implies that h equal to a constant in the entire flow region. H is a constant at all points in the flow region. This is really a very powerful statement, right? But less powerful statements can be obtained under less stringent conditions. Suppose now I keep steady flow. This is now a second set of conditions I am considering. I retain steady flow, right? But I want to look at what happens if it is not an irrotational flow. So I don't want to impose that condition. In which case I get is equal to so for this case, what Aris actually says, and I want to prove that statement, he says that the h equal to constant surface in this case is filled with a network of streamlines, or is covered rather he says, and vortex lines. So effectively this would mean that h is a constant along a streamline of a vortex line. Now what is a vortex line? You've seen what a streamline is, right? If I replace the streamline is one for which the velocity vector is a tangent. If I replace the velocity in that definition by the vorticity vector, then I get a vortex line. So basically, a streamline is one for which the velocity is a tangent at every point on the curve, whereas a vortex line is again a curve in space for which the vorticity vector W is tangent at every point. So when he says it is a constant, so I have to consider any h equal to constant surface. So that means the gradient of h. Suppose I consider h, what can you say then about the gradient of h? Suppose I consider, we are not saying that h is I can always form a surface, because h is this quantity, right? Whatever I have written there, h, right? I can compute that. For steady flow, there is no dependence on time, right? So I can compute, I can consider h then becomes a function of x alone. So the every quantity is a function of x, right? So h equals to a constant, if I just put, it will be a surface in three-dimensional space. Equation h equal to a constant. It will be a surface in three-dimensional space. So what can you say about the gradient of h? The vector that is formed by taking the gradient of h. That's what? It's a normal. What I am actually saying is h of x, y, z. I'm looking at a surface in space. Right? Clearly h is a constant. The gradient vector, right, of the equation dh by dx is nothing but, I can compute this. What does it give? This really gives a normal to the, so it is somewhat different. He's not yet saying that h is equal to constant along a streamline or a vortex line. Unlike what we got here, right? The gradient there is identically seen we're considering a slightly different situation. Impose the condition of steady and irrotational, and I'm getting the gradient of h, the quantity h is 0. Right? Here the gradient of h is not 0. Gradient of h is actually given by w cross v. So the flow is not irrotational. So let's move away from this. Consider a h equal to constant surface. Consider a surface given by h, which is a function of x, y, z, equal to some constant. I can always consider that. That will be a surface in 3-dimensional space. Now you look at the gradient. Don't worry about that equation. There is h equal to 0. Look at this. Clearly, this would be the normal, right, to this surface. Right? So now I have the equation. So what can you say about the quantity w cross v? That will also be parallel to the normal to h equal to c surface. Right? So, if that is normal, that is parallel to the normal. So that would also be normal effectively. Right? But however, right, what can you say about w cross v with respect to w and v? We have seen the cross product of two vectors. If you consider the plane of w and v, let's consider the plane formed by w and v, then the vector w cross v is actually normal to the plane of w and v, the plane formed by w and v. What can you say about the plane? Plane of, yeah, exactly. The plane of w and v is actually a tangent plane at any point to the h equal to constant surface, from which, of course, you can talk about the plane being tangent to the surface. I can't assign any meaning. If you follow the argument given in the Aris, I can't assign any meaning to a line, a vector being tangent to a surface, because effectively that's what is implied by this. But it's possible to show that, because what we are seeing here is that the plane of tangent plane of w and v, right, is tangent to the h equal to constant surface. So the reason why he says it's a network of streamlines and vortex lines is that we know that tangent to the streamline is given by the v vector, right, and the tangent to the vortex line is given by the w vector, right. What we have already shown is that plane of w and v is acting as a tangent plane to the h equal to constant surface. So we need to go a step further and prove that actually, this kind of an argument, leads to a point, but I don't think it proves. The question to be asked is whether h equal to a constant, that is, h doesn't vary along a streamline or a vortex line. That is the question. So what I have done so far is follow the argument given in Aris, but I think it sort of doesn't lead us to directly answer that question. You will see we run out of time. You will see tomorrow's class how, while it is interesting, this is an interesting fact in itself, that the plane formed by w and v actually is a tangent plane for a h equal to constant surface. Rather than considering this, right, just answer some question, but I can directly take and ask, consider an arbitrary streamline, is h constant along that streamline? Why do we have to go to a network of streamlines and vortex lines, right? That's very easy to prove actually. I found it easier to prove. We'll go through this somewhat convoluted argument. We'll prove that in tomorrow's class. But it's certainly possible for you to prove. We have seen what a streamline is, right? That is the one for which the tangent vector is the velocity vector, right? So effectively what you have to prove is that E dotted with the gradient of h is 0, then it's possible to show that the h is a constant. We take that up, I don't want to rush into it. We'll certainly do it in a more relaxed manner in tomorrow's class.